Hey, hello. Welcome back to Short Text 331. Today we're going to talk about eigenvectors and eigenvalues. And this is going to be a part one of our discussion of this topic. Let's start with the definition. So given a matrix A, we say that if there exists a vector such that when you apply A to that vector, you get a constant times the same vector, then that vector is an eigenvector of A, and that constant is called an eigenvalue of A. That's a constant or a scalar. And the important thing about these eigenvectors is that they have to be non-zero. So they satisfy this equation, AV equals lambda V, for some lambda, and they have to be non-zero. And you see this is trivially satisfied if v is equal to 0. So obviously we're interested in non-trivial solutions. So the gist of it of eigenvectors and eigenvalues is this then. When applying a to v, we get a constant times v. And so in a way, this v, each of these v's satisfies this equation for some lambda, have this very special property that when you apply a to them, you maintain the same direction of v. And that's why it's called an eigenvector, or a proper direction for the matrix A. And A will have a number of these typically. And so when you apply A to that V, it keeps V on the same line, on the same direction, or on the same line defined by V. And depending on whether lambda is positive or negative, or larger than 1 or smaller than 1, then it may make that vector longer or shorter, or it may flip the direction, but it's always on the same line. And that's why it's very important to know these proper directions of the matrix A. Now, given A, this identity, this type of thing, only happens for specific values of lambda and specific vectors V, which will vary with lambda. And so typically a given lambda will have a particular vector that satisfies this equation. But it is possible for a lambda to have several vectors for which this is true. And so let's get a little bit into this. So how do we calculate these eigenvectors and eigenvalues? So let's start with an example. Suppose that our matrix is A, B, C, D. It's a 2x2 matrix like this. In that small space of 2x2, the identity matrix is just 1 given by this, 1, 0, 0, 1. Very simple. And our problem, if we put lambda v on the other side of the equation, is AV minus lambda v equal to 0. And we can rewrite that by saying, well, this lambda times v is really lambda times the identity times v. And so we can group this all together into a single matrix multiplying v. That's the purpose of doing this, just grouping this whole thing into a single matrix multiplying the vector v. Now, if this is true, if a minus lambda 1 times v is equal to 0, and we're interested in non-zero vectors that do this, then it must be that the determinant of a minus lambda 1 is equal to 0. If this determinant were 0, if we're non-zero, if the determinant of this combination were non-zero, then the only solution is v equals 0, and we're not interested in that. We want the values of lambda for which this is possible for non-zero vectors v. And so that determines what we call the secular equation. This is our secular equation, determinant of a minus lambda 1 equal to 0. And this expression for the determinant of a minus lambda 1 is going to be a polynomial in lambda, as we will see. And it's called the characteristic polynomial of the matrix A. So in our case, in this 2x2 case, then the determinant that we need to calculate, that we need to calculate to find the values of lambda that satisfy this equation, looks like this. It's the determinant of a minus lambda, b, and then c down here, and then d minus lambda. Because all we did was we subtracted lambda times the identity. So that's why you see minus lambda here on the diagonal. And now we're ready to calculate this determinant. And so it's a minus lambda times d minus lambda minus cb equals 0. And so this is how we need to then solve for lambda. So this is a quadratic equation for lambda, as we will see. And this always has solutions. Lambda may be complex, and that's fine. But it always has solutions. So there's always roots to this equation, at least in the complex plane. They may not be real, but at least in the complex plane, that's always true. It's always possible to find those solutions. And so more explicitly, our expression for our quadratic form is lambda squared minus a plus d lambda plus ad minus cb equals 0. Notice, by the way, that this a plus d here is what we will call the trace of a, multiplying lambda, and this expression here is what? It's the determinant of a that appears here. This is actually always the case for these 2x2 systems. It gets more complicated for higher order matrices like 3x3 and 4x4 and so on. The coefficients get a bit more complicated, but there's always the trace and the determinant appearing here and there. As I said before, this is a quadratic equation for lambda, and because it's quadratic, it will have two different solutions. They may coincide, but typically it will be two and no more than two different solutions. And those are what we call the eigenvalues then. So once we've solved this problem and found the two values that solve this equation, then we're ready to go ahead and find the eigenvectors. So let's go for that. So suppose we want to find v1 that is attached to lambda 1. And so what we do is we go ahead and set up our system of linear equations as before. Let me go back here. We're setting this linear system of equations, this whole thing equal to 0, for lambda 1. Now we've found lambda 1. Lambda 1 is something. We assume that we found it and by solving this quadratic equation. So we insert it in here. So we get a minus lambda 1, b, c, d minus lambda 1, v1x, v1y. Now, I insisted that this determinant was 0. And so if this determinant is 0, it means that these two equations that we're setting up by multiplying the rows by this column in this matrix vector multiplication, these two equations that we get are not independent from one another. So really, we only have one equation, and that's fine. And so that just means that we just need to read the first equation and we're ready to go. And you'll see what happens. What happens is we get a minus lambda 1 times v1x plus b v1y, and all that has to be equal to 0. So we have two unknowns and only one equation. That's okay. That's like that by construction, and it allows us to solve for v1y as a function of everything else. So we solve v1y equals minus a minus lambda 1 divided by b. So I put this on the other side of the equation. I divide by v, multiply by v1x, and so on. I simplify a little bit, and that's it. That's all there is. And so the components of v1, which I had separated here into v1x and v1y, are given by v1x and then this other combination, okay, which I can simplify further like this: v1x multiplying this vector 1 and lambda 1 minus a times b divided by b. That's all I need to know. And based on this, I've completely determined v1, except that, hold on a second, what's this v1x here? What do I set this to? And the truth is you can set it to whatever you want, as long as it's non-zero. You can set it to 1, you can set it to I, you can set it to minus 7, whatever you want is fine. And that makes sense, because if we go back to our defining equation here at the top, you see that if v is an eigenvector of a with some lambda in particular, whatever you want to call it, lambda 1, as we've been discussing just now. So whatever this is, if you take this v and you multiply by a constant, then it's like multiplying this whole equation by a constant, and it's still an eigenvector. And so eigenvectors are really defining directions and in the space where these vectors live, and it doesn't matter if you multiply by some constant in front or not, and you're free to choose the normalization, in other words. So we're free to say, well, we want to fix this constant v1x by hand, setting the magnitude of that vector to 1. And if we decide to do that, we can go ahead and calculate the magnitude of this vector v1. It's going to be v1x squared times 1 plus this quantity squared, and that has to be equal to 1. That's what we mean by normalization. That's magnitude of v1 squared equal to 1. And so then v1x is the square root of 1 divided by 1 plus lambda 1 minus a over v squared. Okay, so that's what we get for v1 lambda 1. But here we did everything entirely symbolically. And so we could have chosen to use indices 2 and 2. And so the same expressions, the same exact expressions hold for v1 and for v2. And so v2 then is going to be a vector of this form, v2x times 1 divided by lambda 2 minus a divided by b. And then v2x, if we choose to normalize things this way, is going to be given by this square root of 1 divided by 1 plus lambda 2 minus a divided by b quantity squared. It's the same expression as here, except that lambda 2 now replaces lambda 1, and that determines v2x, and then our vector will be normalized. But again, this normalization is a matter of choice. We don't have to normalize anything if we're just interested in the eigenvectors, although it's a fairly common choice, and in a lot of programs and a lot of canned routines that you may download, your eigenvectors will be given to you in normalized way. If you enjoyed this video and these vectors, feel free to like and subscribe. And if you're looking for a tutor in physics or in math, in English or in Spanish, you can contact me at shorttext331@gmail.com, or you can leave a comment in the comment section below. And moving on, let's find an example that allows us to study some of these ideas more explicitly. So let's take this example, this matrix H, which I built on purpose so that it has this property that H dagger, which is the transpose complex conjugate, remember, is equal to itself. And so h is 1i minus I is 0. And if I were to transpose it, then the minus sign would appear up here. But then if I complex conjugate it, the minus sign comes back down here, and I get h again. So then h dagger is equal to h. This is what we call a Hermitian matrix. It's an example of a Hermitian matrix. And so let's see what this does. And so we build then our secular equation, our characteristic polynomial set equal to 0. And so h minus lambda 1 is simply 1 minus lambda I minus lambda in the bottom here. And so if I calculate this determinant, I get lambda times lambda minus 1. I just flip the signs of this because they cancel each other out in this expression. Minus 1, this 1 came from multiplying minus I times I. Minus I times I is 1. And so I have a negative sign from the determinant. And so I get lambda times lambda minus 1 equal to 0. And so to solve for that, it's just a quadratic equation. I write it more explicitly here. It's the same equation, lambda squared minus lambda minus 1 equal to 0. And if you use your quadratic formula, which you know from a long time ago, then you get that lambda 1 is 1 plus square root of 5, everything divided by 2, and lambda 2 is 1 minus square root of 5, everything divided by 2. And so these expressions are again a matter of choice. I could have put the minus sign here and the plus sign here, but there's these two and nothing else. So I have these two eigenvalues, and that's all there is. They're both real. And by the way, this is not a coincidence. It turns out that for Hermitian matrices, you can always guarantee that the eigenvalues will be real. So if your matrix satisfies this property that h dagger is h, so the matrix is the same as its dagger, that's what we call a Hermitian matrix, then the eigenvalues will always be real. Let's move on then to the eigenvectors. So what do the eigenvectors look like? Well, the eigenvectors will look like this. We have v1x, that's our prefactor, as we saw before, 1 and alpha 1. I call this alpha 1 to simplify my notation, but this is simply this combination that we have here, lambda 1 minus a divided by b. And so if I use my a, b, c, d values from this matrix, then down here our alpha 1, so our coefficient that goes down here corresponding to this first eigenvector is simply lambda 1 minus 1 divided by I. And the same for v2. v2 is the exact identical expression, except wherever it says 1, we write 2. So we have v2x, which is some constant to be determined by normalization or by some other method. We could just set it to 1. It would be perfectly valid eigenvector. And then alpha 2 then is lambda 2 minus 1 divided by I. Now, I want you to notice something very special that happens, which is true for Hermitian matrix and even for wider classes of matrices, which is that if you take the inner product of v1 with v2, and here we have to be careful because we have complex numbers, and so we have to take the complex conjugate of the vector, then the inner product of v1 with v2 star is v1x, v2x star times, and that's just from multiplying these two guys, times 1 plus alpha 1, alpha 2. So 1 with 1, alpha 1 with alpha 2, but I have to star the alpha 2. The way I wrote this inner product, if I assume that the dot already means complex conjugation, then I don't have to write the complex conjugation here. I wrote it here for emphasis, and so this what I mean by all this is simply what's on the right hand side. So v1 times the components of the other guy, complex conjugated. The point is this: if you have alpha 1 and alpha 2 star here, then let's calculate that. Alpha 1, alpha 2 star is the product of these two things. And so if I star alpha 2, then this I turns into a minus I, and lambda 1 and lambda 2 are real, so I don't have to worry about complex conjugating those. So I get then plus 1 times lambda 1 minus 1, lambda 2 minus 1. So it comes from multiplying these two things, and I with minus I is simply 1. And now, okay, so there's 1 here. Let's look at this quantity, lambda 1 minus 1 and lambda 2 minus 1. If we multiply those two, you will find that you get these expressions, square root of 5 over 2, minus 1/2, and then minus square root 5 over 2, minus 1/2, and you keep doing that, you study that, it's really a quick calculation, you get minus 1. And so you get minus 1, and so you get over here that alpha 1, alpha 2 is, star is just minus 1. And so it's 1 minus 1, and so that's 0. And this is always true for Hermitian matrices. And this is the bottom line. The general rule is that eigenvectors of Hermitian matrices are orthogonal if they correspond to different eigenvalues. And typically, if you have more than one eigenvector for a given eigenvalue, which could happen, then you could orthogonalize those two. But this is then the general rule. The eigenvectors of Hermitian matrices corresponding to different eigenvalues will be orthogonal to each other in this sense. The v1, v2 star is 0. here's another example, a different kind of matrix, 1, I, 1, 0. So what I did here is I broke the hermeticity of the previous matrix, which was 1, I, minus I, 0, by replacing this minus I with a 1. And so this matrix, as you can see down here, is not Hermitian anymore. So 1, I, 1, 0 is not Hermitian. If you take the dagger of this, then the I reappears down here with a minus sign, and there's a 1 up here, so it's a different matrix. And so then the determinant of A minus lambda 1, I go ahead and subtract lambda, and I get this matrix in here. I take the determinant of that, and we get lambda times lambda minus 1 minus I. Now, this tells us right away that lambda has to be complex. Why? Because if I set this equal to 0, there's no way that I can put a real value of lambda and cancel this I, which is an imaginary unit. And so right away, I can already tell that lambda is going to have to be complex. And okay, that's consistent in a way with what I said before, which is that if the matrix is Hermitian, then the eigenvalues have to be real. This matrix is not Hermitian. It could be that the eigenvalues are real, maybe not, we'll see. But in this case, we already know the eigenvalues are complex. Okay, they have to be complex. So now, are the eigenvectors orthogonal to each other? You have to find out. So I'll leave that to you to calculate the eigenvectors of this matrix and determine if they're orthogonal to each other. Remember, if you have complex components for those eigenvectors, which you may very well have, then you have to take the star when you take the dot product between them. So that's important to keep in mind. If you don't do the star, you may get a wrong result, by the way. So it's very important to take take that star and then determine if the eigenvectors of this matrix are orthogonal to each other. They may or may not be. One thing we can say for sure is that the lambda is complex. Now, is there a theorem that could tell something more specific? So I said this general rule. This is actually a theorem. Eigenvectors of Hermitian matrices are orthogonal to each other if they correspond to different eigenvalues, and we also know the eigenvalues of Hermitian matrices are real. So there's a theorem we can state about matrices and the eigenvectors, and it goes as follows. This is a very general theorem. So if A is a normal matrix, meaning that A transpose A is equal to AA transpose, and by the way, this is for real matrices. If the matrices are not real, if they're complex, then it's A dagger A equals to AA dagger. Okay, if you have A dagger A equals to AA dagger, then its eigenvectors form a basis. So then we know that, and moreover, if the matrix is normal in this sense, that it commutes with its transpose if it's real, or if it commutes with its dagger if it's in general complex, then we know that it's unitarily equivalent to the diagonal matrix, to a diagonal matrix. And so that means that there exists a matrix U unitary such that U dagger AU is equal to a diagonal matrix. So this now may seem like we went far astray from what we were discussing. So what's going on here? Why is this important? It turns out that this is very important because if this is true, which is true if A is normal, in fact, A is normal if and only if this is true, that there exists a matrix U such that this is true, then the columns of U are orthonormal vectors that form a basis and are the eigenvectors of A simultaneously. So what this tells us, this whole theorem, what's behind all this theorem that I'm trying to tell you, is that if A is normal, then we're guaranteed that the eigenvectors of A not only form a basis, but they're also orthonormal to each other. So they're orthogonal to each other and they're normalized as well. And there exists then this U is guaranteed if A is normal, and you have this expression that U dagger A U is equal to a diagonal matrix. So what about a matrix A above? Is it a normal matrix? What's happening there? Well, if you take A dagger A, you find that it's 2I minus I1. If you take A dagger, you find that it's 2, 1, 1, 1. And so A dagger A is different from A dagger. And so A is not normal. And so its eigenvector may still form a basis. You may have two linearly independent eigenvectors, but it won't be naturally orthonormal. Because we know that there's this if and only if condition. And so if its eigenvalues, if eigenvectors were naturally orthonormal, then it would mean that we would have this expression U dagger AU equals to a diagonal matrix, and we'll talk more about this and unitary transformations in a future video, and that would tell us that then by virtue of this theorem that A is normal, and we know that A is not normal, and so that would be a contradiction. That's all I have for you today. If you enjoyed this video, please like and subscribe. And if you're looking for a tutor in physics or math in English or in Spanish, you can contact me at shorttext331@gmail.com, or you can leave a comment in the comment section below. And you may have noticed I started to leave links in the description to these notes, so you can access these notes following that link to my website. And that's it. I'll see you next time.